Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Professor Ashu Sabharwal. Ashu got his BTech from IIT Delhi and his PhD from Ohio State University. He's a professor at Rice University currently and also a fellow of the IEEE. So what really amazes me about Ashu is, he's a researcher in information theory, as theoretical as you can get. And then probably frustrated by lack of platforms, he goes on to develop WARP to test his theoretical ideas. And now you find pretty much all the so-called systems researchers universally adopt WARP to test their ideas. And that's amazing. And then what I find is he tells me he gets more satisfaction when his theoretical colleagues actually use the platform, because for a theoretician to find the value in a systems platform, I guess, is even more valuable. So with that, I'll let Ashu, please give him a warm welcome.
You have to be careful what you say over lunch because it gets repeated in the introduction. So I wanted to start by thanking Microsoft. It was a great, when I was approached, I immediately said yes. And I gave a choice of few topics. I said, I can talk about this, I can talk about that. And he said, no, talk about experimental wireless and WARP. So it turns out, so we had actually done two hands-on workshops in India a few years ago, one in IIT Delhi and one in IIT Madras. And they were very good. 2 days you sit and learn how to actually use WARP for actual wireless experiment design and experimentation. So we thought we could just repeat it. Turns out that between our last workshop and now, the customs rules in India have changed. So bringing any hardware in and out of the country is quite hard. So we had to innovate. So this led to an interesting problem. And so that's the end result, this innovation. I'm actually going to, I have a very vague topic. All the other topics I thought were very clear what the topic would be about. Most of you have no idea what I'm going to talk about. All wireless systems have antennas. What is this thing about near and far? And so my objective today is kind of twofold. I want to actually be able to give a little bit of sense that there is no fight between theory and experimental design or systems research. Okay, they're just, in my opinion, dimensions of answering a specific questions. And I'm hoping that I can give you guys some examples from my own experience where following both approaches in some linear combination was very useful to answer the question we had at hand. And then what we'll do with the lectures and workshops, we will actually use all the time to learn. So in my lectures, I would only talk about theory. And in the experiments, you will actually do something which will not look any related to other than the topics, and explore actually how do you explore actual data. You will actually get data by using your browsers from a set of WARP nodes sitting in Houston in real time, and you'll be able to actually start analyzing some data and start to actually get used to the idea of getting real data and how to actually make sense of it. So with these two pieces, I'm hoping that there will be some appreciation that there is a methodology to this madness of research where different people seem to have different flags, that theory flag, this flag. They're all, in my mind, just ways of doing research. Okay. So with that lengthy introduction, I'm going to dive in. So lots of people I want to thank. I think I want to thank when everybody's paying attention, not at the end of it. So of course to Microsoft Research, which in my opinion are doing great contribution to research in India. I hope everybody appreciates it. So I want to actually thank them again. Thank to Mango Communication, the folks who make WARP hardware now. And they actually, because of this logistical challenge that we couldn't bring kits, we ended up building this framework just for this workshop called WARPCloud. They actually built the framework. All the workshop material which you're going to use in the afternoon is designed by them. Actually, I haven't even seen it myself that clearly. And they're actually the one hosting right now. So they're awake in Houston right now. While you guys are doing it, they will be available for support. Of course, to ISC faculty for all their support. And then Nidhin and Akhil, who are I don't know whether they volunteered or they were volunteered to serve as your TAs this afternoon and tomorrow. And so they are actually the local experts here on the workshop material. So feel free to ask them tons of questions. They will be there to support. And thanks to all of you for being a very active audience. I know you'll be asking a lot of questions up front. So with that, I wanted to say a few words before we dive into some details. If you look at the research in wireless, especially or more broadly communication over a noisy channel, that actually has very deep and very useful theories. So the keyword is not deep, the keyword is useful theories. And information theory especially has enjoyed a long period of success. Things which have been shown by theory have translated into actual products. In fact, the first set of this theory to practice translation was telephone line modems. There was a time when telephone line modems continuously improved in speed, and they were all theoretical advances. In fact, if you have heard of the name David Forney, he was an MIT professor who also had a company and was involved in doing this research on both sides and translating it into products. And then with wireless, that trend continued. Quite a few concepts which are there in your phones today actually have a theory backing. What information theory has been very good at has been modeling noise in the channel and multi-user aspects in a system. How do you share spectrum? How do you share resources? To complement that is a network theory, which often has been focused more on modeling traffic side of things. How traffic changes, how do you deliver traffic, quality of service constraints, and how does it impact resource sharing in that sense. So in my opinion, both have been highly impactful in practice. However, there is, as Victor also pointed out, there is often a gap between taking a theoretical idea to practice. This is where I think systems research shines. And they often, the thing is that a lot of theory uses very simple model and have to do so for tractability of analysis. As a result, if you have very complex systems, they're often not easy or even possible to analyze. So then you're left with two options. Either you can simulate your whatever system you're designing, a new protocol or a new architecture, which allows you full control, completely repeatable. So there are some benefits to simulation. But like anything else, your accuracy of the results depends on the models you use in your simulator. Okay. And then, of course, you can go to experiments where you can quantify realizable gains. But experiments are often really complex to actually decode. So I think most people in systems struggle with being able to explain in many cases why the system works the way it works. What is the dominant bottleneck? So I think good systems papers are those which actually not only build the system, show gains, but also explain the why of those gains and what was the bottleneck. So this why part is where generally theory shines very well. So that's why, in my opinion, really there are just three tools as a researcher you have. Either you do a little bit of theory or simulations or experiments as a way to answer a specific question. So the thing to remember is the research question you're trying to answer, and these are your tools at hand to answer them. Okay, so that's why I believe they should be all seen in one light. Now the challenge with wireless experiments, how many of you have some experience with wireless experiments here? Let's say 10%. Okay, so perhaps you guys can relate to it. If you're building any wireless network experiment, you have to work with a physical layer, a MAC layer, perhaps, and they often, if you're actually changing something there, they have different design flows. They actually even things are written in different languages. So there is really generally no single programming environment which allows you to do so, which makes the task harder as a researcher. You have to actually put in a lot of effort before you have an operational test bed. Then, of course, there are complex interactions. There are all sorts of parameters set everywhere. You would have set thresholds and parameters. You have no idea how things are actually getting impacted. So, and on top of that, wireless channels are not repeatable. Okay, so these are just the things as an experimentalist you will have to deal with. Okay, now there are well-known ways you can actually work with these. But some of the top part, I have to say that the community over the last decade has done a good job. Born out of frustration, there have been several platforms which have come about. So USRP is one. I think you guys, most people know about USRP. Definitely a very valuable platform, low cost and easy to work with. Sora from Microsoft, another one, which uses a different architecture, again targeted towards allowing rapid prototyping. And then RiceWarp is another point in that space of platforms which is available for one to work with. So I wanted to give a little bit of history how that came about. I think as a student it's very important to see what happened in the back. So before Warp happened, actually we failed a lot. So again, to re-emphasize Victor's points, often failure is when you learn things, and that generally leads to potential success if you stick with it. Before 2006, we actually had tried many off-the-shelf things, and we have a stock room full of hardware we had bought, which was not useful for experiments after trying out for years. So in the end, we decided we're going to build our own. And that's actually a major undertaking as a university. We generally don't have the expertise to build such complex hardware. Anyway, we got funded by National Science Foundation in 2006. The first team, I was very fortunate to have very good students who designed the Warp version 1 hardware and 2 hardware. They both actually were sold for a while. And then I think what we did was important for making this hardware really become useful. So imagine having a computer with no operating system is useless. It's a just paperweight. So just having hardware is not the end of the story. It's only the beginning of the story for any useful platform. So we actually built full reference design, a physical layer with a Mac layer on top, build a massive amount of documentation for somebody to pick it up, use it, and then lots of education material. And in fact, we did 11 two-day workshops, which I referred to, several in US, 2 in India, 1 in Egypt, and 1 in Taiwan, and then also 1 in Germany. Okay, and now the workshop material has matured that actually we don't need to often hold a online or actual physical workshop. People can just download material online and do it. And perhaps the most crazy thing we did was we actually distributed 80 kits to 35 different research groups from the university. So we were practically selling kits at cost just to our friends. Somebody called up, can you give me 3 kits? Then we'll ask whoever we're working with. They will manufacture, students will in spare time will test it, put it in a box, and then send it out. Okay, that was really crazy thing to do because we thought we'll make 10 extra kits for our friends. That number became 80 in a year or so. At that point, Patrick Murphy, who is the founder of Mango Communication, was my PhD student, decided to take a leave from PhD and say, I think it's time to start a company. University should not be doing it. So he took the 100% ownership of the company. I decided to stay on the open source side to continue growing the open source aspect of it. And then till 2012, he was essentially manufacturing and shipping Warp kits and supporting all the users. And then he's decided that he's going to do the version 3 hardware, which was released in mid 2012. Was cheaper, better, smaller. Became quickly the most widely adopted version of Warp. And then this last year, they released a new version of WARPLab. I'll talk what that is, and a fully operational open source 822.11g design. So you can download this. You can see the whole physical layer Mac and muck with it, and it's completely interoperable with commercial devices. Okay. Now this is a plot I got from Patrick before coming here. So now there are around more than 800 Warp nodes all over the world, around 130 research groups. So you can see many research groups actually have many Warp nodes, so they build networks out of it. And then increasingly every year we see more and more papers actually using Warp to do their research. So we actually maintain a list on the Warp website where you can go see how people in creative ways are using a platform to do their research. I will actually mention the Argos platform a little bit later, which is nowadays what was keeping us busy at Rice. And then lots of full-duplex experiments were done on Warp. And there is a very nice distributed multi-user MIMO paper written, a Mobicom paper using USC. And these are just some of them. At this stage, there are like 150, 60 papers written using Warp. As I said, we actually built different design flows. So because physical layer requirements are different from Mac layer requirements. So over the years, as we needed something for our research, we'll build it and then release it. So this is how all of it came about. So WARPLab is Warp plus MATLAB. So if you know how to use MATLAB, you can actually use Warp from MATLAB, and that's very, very powerful and very heavily used design flow. It actually quickly gets you to doing experiments through MATLAB. It's not real-time system, but it allows you to try crazy ideas in MATLAB with real channels. So it allows you to send raw, transmit, and receive waveforms, and we actually heavily use it for our multi-antenna, multi-node experiments, all on an Ethernet. At the same time, we had built a real-time physical layer, around 10 megahertz OFDM physical layer, which has modes which are not found in any commercial system. So this was again to promote research in physical layers which you can't find in commercial product. So the first line is all the things you find in commercial products. Second is an example of something which hasn't made it to any commercial product, and we will talk about it tomorrow morning a little bit. These are called cooperative physical layers, where two nodes, distributed nodes, get together to help each other at physical layer, at symbol level. And then, of course, the .11 design is available for you to play with. Okay, so that's a quick overview of what WARP is. I recommend going to the website and looking at it for more information. What will we try to achieve? As I said, I'm hoping that we can appreciate there is a nice theory experiments connection. I'm hoping that I can give some exposure to that. But hopefully I'll give some examples where a theory inspired certain practice, and then vice versa, where practice inspired new theory. And in my opinion, a successful research program should try to address all aspects of. You should have theory courses. You should have courses which might use a simulator like NS or NS3, and then also have experiment courses which actually promote experiments. And as a student, I think you should not decide yourself to say I'm a theoretician or experimentalist. You should just solve problems, whatever the right tools to solve the problem is. Okay, so. As was mentioned, actually I'm a theoretician by training. Information theory, we theoreticians are good at abstracting things, and very simple model, trying to get some basic insight, and that's the approach we'll follow for the lecture part. And what we'll do is essentially start with something very basic, which I believe everybody in the room knows MIMO, right? Is that correct? Anybody doesn't know MIMO? If I start with that, nobody's going to say no. Yeah, so everybody knows it, right? And then I will actually go to a multi-user system where I'll actually talk about some new theory results in the context, and their impact will be clear hopefully with a simple example I will give. And this is an example where you have all the antennas on one node and then going to antennas on different nodes. That's where the near and far comes from. And then I will go back in the reverse direction tomorrow, where we will see how far antennas can collaborate with each other. That will be the cooperative MIMO, and come back to this full duplex where near antennas become interference to each other. Now, as I said, since we are short on time, what I will say in lectures will teach something or inform something, and then the labs will inform something else, which are hopefully complementary to what I am doing in the lectures. And then I'm hoping there will be discussions which will help harmonize some of these ideas. So let's get started. The MIMO part is a very quick overview. So there is actually no new concept other than what the massive MIMO research which is going on. I will take only 3-4 slides for that. And then in the second part is where I will introduce a new idea, a new theory idea which came about recently. All right. So for the MIMO, we will just talk about what's the basics of wireless, so that everybody has the same terminology in mind. I think everybody knows here wireless, but so this will be a little bit boring, but hopefully we will have the same notation. And then quickly dive into why multiple antennas help, just again a refresher, and then massive MIMO. Okay. So truly, what is information transfer? Information transfer is equivalent to energy transfer. If you can transfer energy from one point to another, that is the fundamental way you actually transfer information from one point to another. Okay. So how do we do so in wireless? We actually have energy being translated into electromagnetic waves, which is a part of which is what is captured at the receiver, where the antennas convert electromagnetic waves back to current. Okay. So the amount of information transfer you can do is directly related to amount of energy transfer you can do. Okay. So there is an equivalent for us is essentially if you are trying to hear somebody, the closer you are, actually you have more energy transfer from that person, and then if you're farther away, you actually have less energy transfer. That's why the information rate content actually reduces depending on the distance from the speaker. Okay, so what we also immediately know from this picture that the received energy is always less than the transmitted energy. You can't get more than what was transmitted. So instead of looking at actual energy and information, what's more interesting is to look at the rate of energy transfer and information rate. How much sustained energy transfer you can do. So the parameters we actually like to work with is energy per unit time, which is power, and then information with bits per unit time, which is rate, R. So those will be our two symbols we will see in different forms that we would like to work with. How much energy you can transmit per unit time, and at what is the rate you can transmit per unit time. Okay, and then a simplified model really helps. Again, actually completely comes from electromagnetic theory, where this model comes from. Anyway, you have a received energy which is a function of the transmitted signal. So your received antenna gets a power of P sub r. So the amplitude is square root of P sub r, and then it's being received at the receiver, where some noise gets added to the system, mostly because of the circuits, analog circuits in the front end. Okay, the noise is not added by the channel. Noise is actually a circuit noise. Okay, so with that simple model, one can ask this question: if energy transfer is related to information transfer, what is the maximum amount of information rate you can actually transfer at? Okay, so if I can transfer a certain amount of energy, what's the maximum rate I can send it at? Okay, and that's the classic question. It's the first question you start in information theory class. And in information theory class, you of course go through a month-long derivation to get to this formula. But it is the maximum rate at which you can reliably transfer information from one point to another. And note, in this formula, the two things which we talked about are part of the formula. This is the received power. That's the energy transfer rate. And it is directly related to the C, which is the maximum rate we can send at. Okay, that's the information transfer. So now we have linked information transfer directly to energy transfer. Okay, and that's the famous channel coding theorem. This is for additive wide Gaussian noise channels. So if you're an engineer, once you're given this formula, you immediately ask, how can I increase capacity? Two options. There are only two variables, P and sigma square. Two options. You either increase the received power or you decrease your circuit noise. Okay, how can you increase received power? You use a bigger antenna. Okay, it's equivalent of having bigger ears. Or you can have directivity. That's equivalent of holding a horn and sending more directive information, energy in one direction. Okay, so if I can have a directive antenna and align it towards you, I can transfer more energy to you. Okay, so but we know that collecting more power immediately translates into more information transfer. Okay. Everybody with me so far? Good. Yes. The bandwidth, yes. Yeah, I've deliberately kept it to 1 hertz. You're right. Good point. I should mention it in the slides. Yeah. Thank you. And then if you want to decrease receiver noise, where does the receiver noise come from? As I said, from the analog front end. That's essentially thermal noise in your analog circuits, or your analog to digital converter adding quantization noise. Okay, you can improve both. Often comes at a certain cost. And why does reducing noise even at the same power helps you transfer more energy? Basically, when you have noise, whatever you transfer is getting perturbed by noise. If you have smaller noise, the perturbation is smaller. Allows you at the receiver end to distinguish between two signals better, and that allows you to pack things more in the same space. So that's why you can send more information. Okay. Okay. So that's the basic famous formula. In practice, we all know wireless doesn't work that way. That's the free space design. Wireless, when you actually send any electromagnetic wave, in practice you will have reflections. And in fact, even worse so that the environment changes with time. So either the reflectors or the transmitter or receiver are relatively moving. We are all like bags of water. We are 70% of our body is, I think, water. So we actually are very good reflectors and absorbers of energy. So we moving actually changes the wireless signals from the AP. So what that leads to is a time varying multipath, which is the multipath signals changing, leads to this fading system. So you actually, this is what you will see, that the received power as a function of time is not constant. Okay, it will be varying because something is moving in the environment. So either the transmitter is moving, or the receiver is moving, and or the environment, your reflectors along the way are moving.
Can we model such a wireless channel as a linear time varying system or
it is a linear time varying system because it follows, yeah, it follows Maxwell's laws, so it is always a linear system.
linear?
Yeah, unless you actually remove, diffraction. Diffraction is not so. Yeah. But that's the typical model we use, linear time varying system.
Some capped delay line model.
Yes, yeah, that's like the most basic thing. Yeah, and it's quite accurate.
Now harmonics introduced once we do a particular transmission, and as a consequence of that, there are non-linear components.
Right, absolutely. You're talking about like an amplifier going, yeah.
To set the context, Sachin actually had this slide where he was showing how the nonlinearity is introduced because
Right.
of amplifier effects and ADC quantization and all
So
those.
we cannot accurately model our channel as a linear time invariant system.
The channel is still linear time invariant system. This is the wireless channel. What Sachin was talking about was what happens at the transmitter receiver. Now you can choose to include in the whole channel, then you will get a nonlinear system. Or in this case, you're only quantifying what the actual propagation from the antenna to the other antenna is. So energy leaving from an antenna, energy getting received at the antenna. This is what this model is about. But you're right. Once you decide that I'm going to make a digital to digital model, what was sent digitally and what was received digitally, then you have to deal with all those issues. Okay. Now also, this is actually very important. I'm glad this question was asked. So for self-interference, those are the dominant effects. Okay, and so actually modeling them is an important thing. So that's where you need to understand what really happens in an actual system, and what are the dominant effects which actually impact your performance. However, for a transmission like this, where you're sending from one node to another, those are not the dominant effects. Your loss, which is the loss due to transmission, movement of the environment, and the receiver noise, those are actually the dominant effect. That's why we actually ignore nonlinearities and ADCs. Okay. So theory often is very, first thing you do is you don't model everything. You say what are the dominant things which actually affect me, then I will only model those. That will give you first order accurate answer. Okay. Then if you decide you want to have to go, those you do have to quantify other things, then you will actually have a more complex model. Okay, so what does this time varying model do? That you actually have, because you're getting more received power at one point or less received power, that's what this y-axis is. You can say more received power is good because you can, we immediately saw that receiving more power is good because we can get more information at that time instant, and then less is bad, right? It's kind of true, universally true. So that's why we label good channels and bad channels in a time varying system. Okay, so our received power has a time varying nature to it, and that's why we have a fading channel models or signal models now, where you have a received signal which has an amplitude which is time varying times whatever was sent, and then you have a noise component. A more common way of writing is to decouple the power part with the multiplicative factor, which amounts for the fluctuations we had, and we will then write distributions, probabilistic distributions of how statistically that multiplying factor changes. Okay, so this is an example of Rayleigh fading, which is commonly used, modeled for a lot of wireless propagation. Okay, so now we have to ask the same question. So we ask the question that if I gave you a model y equal to p times x of t, square root of p times x of t, what is the maximum information you can transfer? And that was a Shannon's coding channel capacity formula. You can ask the same question. Now you have a channel which is not fixed. The channel itself is changing with time. What's the maximum rate you can push through this? Okay. Turns out there actually are now, over the time, we have developed multiple metrics for quantifying capacity, and the two dominant which are studied are related to whether the traffic is delay sensitive or not. Okay, so if you're talking about voice traffic which is delay sensitive, then a model where you have to send a packet and immediately decode it is a better model to worry about. So that's where the notion of outage capacity comes in, that you have to send information and being able to decode within a certain deadline. For that case, we define the notion of outage capacity, which is intuitively as follows, that if you're sending packets at a rate r, each of them coded at a rate r, and then these packets are traveling from the transmitter to receiver over a time varying channel, you may encounter that one of the packet goes through a channel where the received power is not sufficient to support that rate r, because the capacity at that moment is actually lower than the rate itself. Okay, and the channel coding theorem goes both ways. It says this is the best you can do, and if you try to do more than this, you can't send anything reliably. That's the powerful part of the channel theorem, the converse. Okay, so if you have a bad channel, it leads to the lost packet. So that allows you to actually define this notion, see it in this term, that if your channel capacity itself is now time varying, and you can use the same formula, where now you have replaced your received power with the power term, the constant, and the magnitude square of the channel coefficient. Okay, so what you're talking about here is that now you have channel coefficients which are changing with time, and then some channel coefficients are bad, the number is too low, gives you low capacity. Okay. All right. So since we know the channel capacity is time varying, so the outage capacity is defined as what the rate at which you are sending these packets, or the actual rate at which these packets are encoded, times probability, how often your capacity itself is greater than the rate you are sending it them at, encoding them at. Okay, so this is basically good put in different literature, that you sent a packet at rate r, what's the probability it will make it, that the channel will be good enough to support it. That means the channel allows enough energy power transfer for it to be able to decode it. Okay, you can rewrite this probability of success of getting a packet as 1 minus probability of failure. That is, your capacity drops below rate r, and that is often used phrase in cellular, which is probability of outage. What's the outage? How often you will lose a packet. Okay. So your outage capacity is directly related to what is the success rate you have of being able to send those packets across. So actually this afternoon you will do some exercises, very simple exercises, which you will get this probability of outage, which we'll call frame error rate or packet error rate in your exercises, but they will be actually quantifying this number for different modulation, which is equivalent of sending at different rates. Okay. Okay, so one question one could ask, if you look at this formula, if you point, should we increase R or decrease R? So let's say we increase R. So would somebody want to comment on what happens to the outage capacity if we increase R? This increases. What happens to this? Everybody understand why is that the case? Okay. But the product, we don't know how it will behave. This is increasing, this is decreasing. We don't know how the product looks like. Sorry? Very good. And then if you decrease, this decreases, that increases. So actually there is a sweet spot. And that sweet spot depends on the distribution of h of t. Okay, so inequality will of course get you some bound. But you can actually find a sweet spot. In some cases you can actually solve this, that what is the rate you should choose if you know a certain distribution of your channel. Okay. Now as I said, there are two metrics which are used. One is the outage capacity, the other one is the ergodic capacity, which is good for delay insensitive traffic. Okay. So here is this is where theory shines, is to create mental models which may not be possible. So here is, let's say we have a traffic which has no delay constraint. Okay, I have a bucket of bits, infinite bucket of bits. I need to transfer them from one point to another. reliably. That means the other side can decode and decode them as the same bits they are here. And I know my channel is changing over time. I have no constraint. Take forever you want, but I would like to get them across. Okay. What is the capacity in this system? When you have no decoding delay constraint. Okay. Turns out in this case, this is the notion of ergodic capacity. In this case, you will actually not just force yourself to decode after the end of every block you send. You will actually send lots and lots of bits over long time and eventually decode it. You kind of wait forever and decode at the end all the bits together. Turns out that's the right thing to do. And then in that case, your performance is then determined by the average channel characteristics. It's no longer determined by what happens at each time moment. In outage capacity, we are determined by the channel for this block or packet was bad, hence I will lose it because I need to decode it immediately. In this case, since you can wait to decode, you can recover some of it later on. It depends on how you code the system. Okay. So concepts inspired by this ergodic capacity are actually used in systems. A very reduced version of it. If you think about it, ARQ and others are actually using channel variations in a certain way. Of course, they have feedback, which is slightly different from this model. Okay, but I won't go into that. We will actually revisit some of this tomorrow. So let's go back to our outage capacity. Okay, so we have a outage capacity which is rate, where times how often you can get the packet through successfully, and then C of t is essentially so remember there is a probability distribution over h, and we have a term inside which is mod of ht square. So what we would like to do to increase this capacity, we have to somehow change its distribution. We have to make this probability more favorable. More often you should get something across. Okay, and there's one way of doing that is using multiple antennas. Okay, so how does that work out? So imagine now you have a receiver which has multiple antennas and perhaps the same environment, and now you're getting two signals at two different antennas. And in this case, if these antennas are sufficiently separated, what has been observed in practice, that you would be able to get channel variation over those two antennas which look statistically uncorrelated. Okay, that what's happening at my antenna when the channel goes bad or good is not the same times or not related to what's happening at this next antenna on the same device. So for example, your new smartphones, iPhones and Galaxies, most of them have two antennas now, receive antennas for cellular systems. Okay, and they are essentially leveraging this principle. They are getting the same signal to two antennas and leveraging it to get a higher reliability, and essentially changing the distribution of that h. Okay, so why does, if they are uncorrelated or independent, in this case actually you can show they are independent, that then the probability that both channels are bad is probability that each of these channels is bad times square. So that the total probability you get a bad channel aligned up is smaller than each of those channels independently. This is the equivalent of adding redundancy into any system. If the system fails with certain probability, you add a redundancy into the system, the total system failure becomes epsilon square. Right? RAID arrays work the same principle. Okay. All right. So in fact, you can write this. This is the most complicated slide I have over 2 days. With one receive antennas, we said the probability of failure, which is outage. So I'm talking about outage probability now, not capacity. With one receive antenna, your probability determines is that this log term is less than rate r. That means you sent something and it was less than your desired rate. You can turn this around and that this h of t squares is less than this threshold, which is inversely proportional to SNR, average SNR in the system. So SNR is just PR over sigma square. When you have two receive antennas like I described, what you can show is that now the right formula for you is outage probability is sum of both random variables h1t square plus h2t square less than 2 to the power r. Same coefficient, same threshold. That is same as norm of h. Okay. So you can see now your total left side has actually increased. So it will be less often that you will be less than this quantity. So your outage probability will go up or down? Down, yeah. All right. So what this does is that the received diversity leads to power gain. You essentially gain power. Another way of looking at it is, I had one antenna, I was getting certain amount of power. I put another antenna, I get more power. Okay, and in this case, that power just directly translates into higher mutual information or higher capacity term, where you have log 1 plus norm h square of that same SNR coefficient. Okay, what's the way of actually getting this, reaching that term is actually very simple. If you have one of the antennas receiving where the channel coefficient is h1, other one receiving with channel coefficient h2, so the received signals look like this. I've dropped t's here. So y1 is h1x plus noise, y2 is h2x plus noise. All you need to do is take these things, combine it by multiplying this by h1 conjugate and this by h2 conjugate, add them up. That is a right combining way of combining both the signals, which leads you to that power gain. Okay, so that's receive diversity. That's why receive diversity helps. Okay, everybody knew this. Okay, just a refresher, as I said, transmit diversity is a dual of this. So instead of having 2 receive antennas, now I have 2 transmit antennas. So to think about that, I was receiving, now I need to send a packet back. So instead of having 2 receive, I have 2 transmit antennas. Transmit beamforming is the dual of receive diversity, which you just described. So instead of waiting the 2 signals after you received them, you wait the 2 transmit signals before you send them. So you will have h1 conjugate of x going from 1. It's the same signal, but you are weighting it differently. And h2 conjugate of x coming from this antenna. It goes through the 2 channels, h1 and h2 in this case. And then you end up with, so this is what you are actually sending. You end up with, again, norm square root of prx plus noise at the receiver. Okay, so instead of in the receive diversity, you were combining them after receiving them. In transmit diversity, you combine, and then the channel adds them up for you because you have single antenna. Okay, so that's what channel is adding up signals for you. Okay, so this leads you to same mutual information. That's why I say it's a dual. You actually get the same mutual information with transmit beamforming. So 2 antennas transmitting and 2 antennas receiving actually again lead to this duality. Okay, this is also called beamforming. You're essentially, if you look at the spatial pattern after you've actually done this processing, you will find out that there is more energy being directed at this antenna, receive antenna, and less so in other direction. Okay, the 360-degree integral always has to be the same power. So if you want to increase power in one direction, you have to steal from other directions. That's what beamforming essentially does. Okay, and it's called beamforming for obvious reason. It looks like a beam. Okay, so that's the refresher. Now where are we going with all this? So if you do you guys know what .11 AC, 802.11 AC, right? How many of you know what's the big differences between the previous generation of .11 and AC? Multiuser MIMO, yeah. So actually that's again something which was there, was suggested in theory many years ago. We studied for a while that if you, and the reason for studying that was as follows. So one could do MIMO, which have multiple transmit antennas at the one end, at the transmitting end, and multiple at the receiving end. However, with small form factor devices like phone, putting 2 antennas was already very hard. Putting more is just not possible. Okay, so how do you use something which has large number of antennas, your infrastructure node, and get multiplexing gain out of it? Somehow send more information streams. And multi-user MIMO is one common way, one obvious, well not obvious, one way of doing it is to, you essentially beamform to multiple users simultaneously. So instead of just sending one data stream to one user in one time slot, in the same time slot now you can send multiple data streams to more users. Okay, so in this case, if you can think of this system as multiple antennas here on the transmitting end and multiple antennas on the receiving end. It's just that those antennas live on different devices. Okay, but you're actually using the same MIMO concept, but thought differently. You still have a matrix which you need to work with of channels, which allows you to actually support such a concept. And a common way of doing so, if you want to keep the receive processing simple, is to use a beamforming method, multi-user beamforming method called zero forcing. What that does, it adds one more constraints. You want to send information in one direction, but you want to send no energy which is intended for this user to any of the other users, because they're not interested in that energy, in that data stream. So you want to zero force. That means you want to make sure that you send zero information of this user to any of the other users. Okay, so you create nulls. That means you create such that there is no energy being sent from this data tree to any of these streams, and that's called zero forcing beamforming. And we know that if you have L antennas on the infrastructure, K users, you can support a minimum of L, K data streams simultaneously. Okay, that is called multiplexing gain. And the way to improve multiplexing gain is, of course, to increase L number of antennas. Then you can support higher number of K. Okay. All right. So that's where I think .11 AC supports maximum of 8 antennas, and LTE, for example, has at least in standards up to maximum of 8, if I remember correctly. But most LTE deployments or 3G deployment don't use more than 2 or 4. I think only in some European countries they're actually thinking of 8. So we are kind of limited at less than 10 numbers in actual system. What if you had huge number of them, perhaps 100 antennas? Okay. So this zero forcing is actually quite difficult to do computationally. Turns out if you have a very large number of antennas, then a very simple idea, which is the transmit beamforming used for one user, which is also called conjugate beamforming, becomes actually optimal. Okay, so you don't even have to do zero forcing. You can use the same idea, just send same beamforming idea for each user, and then just add them up. And that was actually proposed by this paper by Marzetta, which had looked at the limit of it, that if you take this base station with arbitrary number of antennas, what can you do? Okay. All right, so turns out that it's a beautiful concept. It has tons of challenges. One of them is, as you can imagine, when you make something so big, you have more antennas. That means you have more channels to learn. More users, again, more channels to learn. So you essentially have order km channels to learn. Remember, in transmit beamforming, you need to know what the channel coefficient is for you to weight it correctly. If it's H1, H2, you need to H1 conjugate, H2 conjugate. You need to know the channel. That learning process becomes problematic. Let's say if you have 100 antennas with 50 users, that's 500 channels you have to learn. And they are time varying, right? So they're changing with time. But if it is possible to do so, then there are great gains available. So this is a paper written by folks at Rice, my colleague Lin Zhong and his student. Marzetta was, some Bell Labs folks were also involved, which actually looked at this experimental results, which looks at the total capacity in bits per second per hertz and the number of base station antennas. And you can see there is an increase, continuous increase when you're using zero forcing as the number of antennas increasing. Even simpler techniques like conjugate beamforming does give you an increase, of course less than zero forcing, but there is a value to having more antennas. Okay. So if you, in case you guys were wondering how did they go up to 64, Clay Shepard actually built it. So this is the version 1 of the Argos array we have at Rice. This has 64 antenna arrays. Each of these are actually driven by a warp board in the back. So this is how the scalable nature of warp actually helped. And then there are actually, for the first version, they have 17 warp boards driving these 64 antennas. 17th board is actually doing clock synchronization among all of them. So the version 2 of this array architecture, actually now we have 96 antennas which can scale to 144. What it allows us to do is to ask and potentially answer what if questions. If you had so many antennas, what could you do with it? You may never see an actual access point with so many antennas, but it can possibly be a useful tool to answer questions which you may want to ask. Now with move to higher frequencies, more antennas are also becoming quite viable. So 60 gigahertz, 100 gigahertz, the wavelengths are smaller. You can actually people are already packing 40 to 48 or 64 antennas in arrays. So this is where actually the trend is going to be. Again, hopefully some of the wisdom we gain from here might be transferable at those frequencies, but those frequencies have their own interesting challenges. Okay, so to support all this, as again, as we were doing this research, we found there are certain other tools we need to even do the research, and those massive MIMO tools are also available on warp.rice.edu, that if you want to do experimentation with large arrays, large could be 8 antennas, 16, 32, whatever that number is, then you can actually use those tools which are now geared towards large array systems. Okay. Sure.
At very high frequency like gigahertz, there will be problem non-linearity at the amplifier side.
That problem is always there. Yes.
How it's already there.
Yeah. All amplifiers pretty much have a nonlinear regime, the ones which are used in practice.
No, at the very high frequency.
Oh, you mean like 60 gigahertz and on?
60 gigahertz.
Yeah, absolutely. Yeah. They often also transmit very small amounts of power. They're not very high power systems. Yeah. Okay, so actually with that we are done with the MIMO part. I realize I'm running a little bit slow. But I wanted to actually move to the next part if there are no more questions, which is the far antenna aspect. So if you don't build a system which has only one user, you will have a system which has multiple users. So the question you can ask is, what's the best way of supporting all these users? Again, an information theory attack would be, I would first have to create a signal model. What is the energy transfer equation essentially, or power transfer equation? In this case, again, we can use Maxwell to drive this. You actually get, when you send two signals, they actually linearly add up on the antenna. That's why you get this received signal, which is some channel channel multiplied by your own signal, another channel multiplied by a second signal in noise. Okay. So in this case, two signals are being added up. Okay. So that's what the receiver sees. The receiver has to now make sense of data from the two signals. Okay. So you could actually say, I'm going to send this at rate R1. My rate information transfer will be rate R1. Here information transfer will be rate R2. And then the question, instead of asking what is the highest rate, you ask what are the all possible best rate pairs. Okay, so you will have rate pairs R1 and R2. What are all these things I can support? Turns out that is also very well understood. For additive white Gaussian noise channel, that region actually is a pentagon, which actually is driven by only 3 inequalities. That the best you can do on R1 is same as the capacity you could get for a single link, right? This is exactly the same formula, log 1 plus p h1 squared over sigma square. Whatever you could do best on R2 is the same thing, depending on what receipt power you get from user 2. And turns out that the sum is now determined by the sum of the total powers. That's actually a little bit counterintuitive. It actually requires a proof, and it's not very straightforward to immediately understand if you're not used to the idea. Okay. However, you do see that this now region is shows that there is a resource coupling. That if I want to have a high rate for myself, R2 has to go down. Vice versa. If you want to increase this, R1 has to decrease. That means we actually share the resource. We have to now, there will be no resource sharing issue if this was a square. That means we could send both at our maximum rate. That doesn't happen in this case. Okay. So what's very interesting is, so if you actually plot another thing, this is just time sharing. Okay, so time sharing is that you use a certain fraction of time and I use a certain fraction of time. Whenever we send, I send, you don't send anything. Whenever you send something, I don't send anything. That's time sharing. What is the time sharing capacity region? Is just this triangle box. But the capacity region I just plotted out is bigger than the triangle box. Okay, so actually the corner points tell us that you can actually slip in more information without backing out from the other user. Okay, not non-trivial. It's not clear how you actually do this. Okay, but the best you can do is actually better than time sharing. So there was a whole literature on this to actually exploit this in system called multi-user detection. In 90s, that was a big area. Many people became IEEE fellows, writing paper on it, or become NAE members, which actually translate this into actual practical system. Nokia's and Ericsson spent tons of money actually building it, and it wasn't very practical, unfortunately, when you have to implement it. But only recently in Qualcomm eventually showed a 2-user system where 2 users can actually talk at the same time. However, that did not become part of LTE, so Qualcomm had to shelve it. But it's possible to do in an actual system with high mobility and all those things. Okay, but I'm going to actually talk about a different challenge. So if you look at the Pentagon region, there is a challenge to achieving this capacity region. Okay, we have 10 more minutes, then you guys can walk around and do your workshops. So let's everybody wake up for next 10 minutes. All right. So how do you get this capacity region? It actually requires you to have a global knowledge, perfect knowledge of number of active users. That's how you can actually draw this region. And also you have to know what this H1 and H2 are. Again, you have to know the knowledge, channel knowledge. Now for a 2-user system, that seems like a trivial thing. 2 users, I can measure them. However, if you think about any large network like cellular network or even infrastructure .level network, this is just impossible for you to know all the channels for all the links, because that's what you need to know to be able to draw capacity regions like these. There will be, of course, even more dimensions, right? If there are 100 users, this capacity region will be 100 dimensional. Okay, but to draw it or to write about it, you will actually have to know all those 100 channels at one point. Okay, so no single entity in these systems, whether they are centralized or random access, actually has the full information about the topology of the network or the channels. So that's the reality of the system. Okay, so question is, how do you decide rates in this system? Okay, so it's actually kind of a practical problem. Turns out information theory has never looked at this problem, which was surprising. So this is where I think perhaps because I worked in Mobicom community, where I had understood a lot of practical issues in building systems. One of them being that you have to make distributed decisions. So around 2006 or 8, we started asking, what is the capacity of making distributed decision? Okay, so I want information theoretic capacity, that I can do anything I want, but I have to make distributed decisions based on local knowledge. That question turned out to be easy to pose, but very difficult to answer. There were no tools actually available for us to use, and took us several years of hit and trial in theory now on paper to actually come to any meaningful answers. So I'm going to give in 10 minutes an overview of that interesting answer we begin to find now. Okay, so first of all is the modeling. How do you model things? So the natural way of modeling is, this is again completely derived from what happens in protocol community, is that nodes often just have a local view of the network. I may only know 1 hop channels, I may know 2 hop channels, right? Depending on what protocol I implement or for learning the network, I may have a certain hop knowledge of the network. We'll call it a local view of the network. The thing is that local views are mismatched. What I know about the rest of the network is different from what my neighbor knows, because my neighbor knows the 1 or 2 hops channel information from away. Okay, so it immediately you can see this model leads to, if I have to make any decision about transmission and reception, they will be potentially different and conflicting with what my neighbor decides to do. Okay, so lots of actually interesting problems which happen in protocol design are all because of mismatch of knowledge. You know, even collisions are because of mismatch of knowledge. I should not, if I knew that you were going to send, I wouldn't have sent it, right? So, but we are asking not just under any circumstances, if you could design any physical layer, any MAC layer, as long as you have distributed local view, what should you do? What is the optimal global performance in information theoretic sense when you have to by necessity do distributed allocation? Okay. So it took us a while, as I said, 2-3 years of hit and trial. But in 2009, I think we're beginning to actually start to, came up with the models, first set of questions. And around, in last few years, we actually had some interesting results. So I want to give one very basic interesting result from that, going back to our example. Okay, but here is an example which is where the practical constraints were always there. In fact, there are communities which have done this research, but the theory was not there actually to model those practical constraints and actually to take it forward. Okay, so again go back to this simple example. What happens in this simple example? If each of the nodes, the transmitter only has one hop knowledge. One hop meaning transmitter 1 only knows its own channel H1 and transmitter 2 only knows its H2 channel. Okay, and I have to decide what rate I should send at. I don't know what the other, I know there is another user, but I don't know its channel. Hence I don't know what capacity it can have and so on and so forth. So what do you think will be the one hop capacity region? If any of you have to take a guess. I'm asking for a lot, but take a guess. Yes, is synchronized. A good question. Assume it's synchronized, in time synchronized, but that's all you have. Sorry, you were going to say something? You multiplexing the channels? Yes, I think you're right. Yeah. So if I understood you correctly, I think you're saying that the capacity region is actually just again time division. So is that what you meant? Okay. It's a good idea to agree. Yeah. Since the answer is already on the board. So it turns out that the full knowledge capacity region is this pentagon, very famous pentagon. It's in textbooks. But the one hop knowledge capacity region, and that means you can design any coding scheme. Doesn't matter. You're not restricted to anything. It's not QAM or this or that. It's just any coding scheme you can have. And then this is what the capacity region will turn out to be. You can't beat TDMA. Okay. Question is why? Okay. So we'll look at a very intuitive answer to that. But this was actually just a warm-up example in this paper. So in the paper we looked at an interference channel, which is a lot more complex than the two user channel I drew, and I asked the same question for those channels and actually gave an examples of where we can actually completely derive the capacity region for those systems. Okay, so what's happening? Why is this turning out to be optimal here? So if you look from the transmitter 1 point of view, you know, to actual pentagon depends on these inequalities. So if I say I am transmitter 1, I want to draw the pentagon, but actually it can't, right? It doesn't know, it knows its own rate, which is this inequalities, but it doesn't know either of the two inequalities. So the pentagon could look like this, the pentagon could look like this, pentagon could look like this. What should it assume about the other guy? Okay, if it assumes the worst case scenario, turns out you should assume that actually you know nothing. So the only thing you can actually really do is time division, because that requires no knowledge of the other channel. I know for sure that on this, if I just send for a fraction of time, whatever I want to send, I'm not going to collide with my other user. In that case, I know exactly what the capacity of the link is, and I will be able to reliably send information. Okay, so this TDMA becomes the only approach. And in this case, of course, as I said, we are assuming the number of users, we are assuming synchronization. But what you see is that partial information has reduced the capacity region from pentagon to a triangle again. And actually many practical systems are TDMA. They are actually time sharing system, or you can call them, or FDMA. They are orthogonalized systems. So only one user send at a time. So they may be actually optimal, close to optimal, till you change the information infrastructure. That means architecture. What information is available to whom? Till you change that, they are actually nearly optimal, or optimal in some cases. Okay. Now I think you were bringing out a very important point, and I will quickly address that. In practice, you have random arrivals. So the traffic is bursty. That means you may have time slot 1 where these two guys have packets, but perhaps later in time these three nodes have packets. So the number of users is often changing over time, and that's why you don't actually know how many users in the system who have packets at any given time. So then you actually also need a method, or have to somehow pay a price for coordinating who goes next, even in a TDMA system. You cannot decide upfront what fraction of time I will have available. Okay, so that we have not modeled in theory, so I don't know the exact answer to that. We haven't found an easy way of modeling it. So it remains an open problem. If you don't have any coordination or the number of users, what is the information theoretic capacity? But if you look, we already have protocols like your .11 trying to do this in a distributed fashion. So there is either you can do polling or you can do a random access, where each terminal then uses a random start time, essentially randomizes their start time and hopes that only one of the nodes will win the medium, automatically giving you a schedule, a TDMA schedule. Okay. Now we know that dot 11 is not a perfect coordination. Actually, you will see some examples of that in your exercises today. But it's very simple, highly scalable protocol. Tons of literature, and as I said, the exercises this afternoon will allow you to explore dot 11. But you can actually draw the capacity region of dot 11. Actually, it looks like this. On the same plot, if this was the full knowledge, this is one half knowledge, this is a distributed coordination. Okay.
So there is always rateless codes and all those things that are coming up, right? Let's say I have two users and I just let them pump, and I hope that I'll be able to use rateless codes to get both these despite interference. So can we achieve some kind of capacity there?
Yeah, it will be higher, but rateless codes have implicitly slightly different model. If you're talking about the same thing, they actually have a feedback from the receiver to transmitter. That's not model. This is zero feedback system. That's why the answers are often very conservative. The moment you introduce feedback in the system, you can start to recover some of this back. Rateless codes are stopping based, right? Stop now, and so you have at least 1 bit feedback, which will totally change. And feedback is also known to actually increase multi-user capacity regions. It doesn't do it for single user, but it does it for networks or multi-user. Okay.
We assume that we don't know channel of other guys.
Right.
So does it mean we don't know the distribution at all, or we just know distribution but not the realization?
Yeah, good point. So if you know the distribution, the answer is different. In this case, it's actually there is no distribution on this. This is a compound channel formulation. And the reason for saying that is that what does the distribution in practice depend on? In one way of modeling is average SNR, which is equivalent of distance approximately, right? So if I know nothing about the other user, I should not actually also know their average SNR. So then I don't know their distribution, because that's the parameter in the distribution. That's why the model is what is called a compound channel, which is like really the worst case scenario. That's why the answer is so pessimistic here. Okay, but if you think about it, dot 11 like systems are designed that way. They are essentially have no knowledge of what the other guy's links are, right? And they are of course solving the coordination problem, like how many are they competing, but at the same time they have to deal with lack of other people's channel knowledge. Sure.
So you're talking about feedback, but then this DCF in some sense gives you feedback for collision avoidance and everything.
Right.
So is there an intuition to say that you can do better than DDMA in that case?
Yeah, the good point. Yeah. So the thing is that feedback, after I said it, so I'm glad you brought it up. Feedback is what is carried in the feedback, I think, is the important thing. So that feedback is only for coordination, the way DCF is organized. It doesn't tell you anything about other guys' channels still. Unless you can start to infer that and actually encode it, you will actually are still only trying to get to TDMA, but you will not be able to move beyond that. The perfect coordination is where you will, this is perfect coordination system. Okay, so actually I'm a little bit over time, so I just have a few notes for this afternoon workshop. So this is the WARPCloud, in case you're wondering how it looks like. So this is in Mango Communication offices. They have a bunch of tables with tons of nodes where different configurations actually are set up so that you can do different experiments. So they are actually hardware different configurations. But your access to is through a browser. Your handouts actually already tell you what to do. So all experiments are real time. That means when you submit something, that actually something will happen on the warp board. A bunch of data will be, statistics will be collected and sent it back to you through your browser. And their time multiplexed among groups. So if more people submit experiments same time, the delay for you guys will increase. Okay. So this is actually, so I wasn't sure whether Nitin will be here or not. So I wasn't sure who the TAs are, but your TAs are sitting right here. Maybe you can raise your hands. So that's Nitin and Akhil. They know all the experiments quite well. There are two sets of labs you will do today. MIMO lab is quite easy, but that's just for you to warm up. So I think we'll take around 90 minutes to do it. In 90 minutes, you should be able to run all the questions and perhaps create a preliminary report in Google Docs. Again, instructions are there. The interference channel one takes a little bit longer, so we'll probably spend whatever the remaining time today, 2 to 2.5 hours. I think the groups are already decided. Yeah, so they have a group list. Perhaps you guys already know. It'll be good if only one person is submitting experiments from your group, and others perhaps are, writing a Google Doc report simultaneously. I'm hoping that everybody will write a report, so at least they can actually start to form and answer key answers for themselves. And so we will have each group will actually generate 2 reports, one today and then another one tomorrow. Please use one of your accounts and then share it with the account which is listed on your handouts. Let's see. So I think we have said that the WARPCloud is actually scheduled, so only supports around 25, maybe maximum 30 accounts. So please only keep one browser login per team. Okay. So I think that's it. Are there any other questions based on what we have talked so far, or about the workshop, or the hands-on things? All right. Sounds good. Oh, you have a question?
So can it be hello? The RAP board work with MATLAB. So can we work with the Simulink also?
Yeah. So
only M file or Simulinks?
So actually, the whole physical layer is written in Simulink. It's a Simulink.
Yeah.
It's a Simulink file.
Yeah.
But it uses what is called Xilinx system generator blocks.
Okay.
So those are blocks supplied by Xilinx, which are you can actually have in Simulinks. But the Warp lab itself is only through MATLAB. Probably you can write it through Simulink, but I don't think anybody has ever tried it, as far as I know.